All right, welcome back. Good morning, good afternoon, good evening. Friday, March 6th. Moving on now, 4.3 was, again, very tough, very difficult, very frustrating. Hopefully you had a chance to kind of spend a little time with the different derivative tests, apply them, look at them, what do they mean, what is it telling you, and to be able to answer all the questions. Can be kind of tough. Remember, if you're having a hard time, if you just don't understand the answer in the back of the book, go look at that student solutions manual that's sitting over there on top of the 4-drawer filing cabinet, and it'll give you the first couple of steps. It'll show you the tests and kind of explain a little bit about what's going on. But for right now, we're moving on. We're going to completely switch gears. We're going to look at something called intermediate forms, and dealing with intermediate forms using something called L'Hopital's rule. Yeah, I know, it looks like lay hospital, right? But it's L'Hopital rule. L'Hopital was a French, well, I don't want to say he was a French mathematician. He really wasn't. He was kind of a poser. He was just a very rich person, a French nobleman, the Marquis De L'hpital. And what he did was he sponsored many other mathematicians. He paid, for their lives. I mean, he could, he paid their rent and for their food so that they live and that they could discover and work on stuff and go to school and learn different things. But the idea was that L'Hopital, as their sponsor, if anybody ever discovered anything, he would publish it under his name, and it became his property, L'Hopital. And this is a perfect example of this. L'Hopital's rule was not discovered by L'Hopital. It was one of the Bernoulli brothers. Johann Bernoulli actually discovered it. But Johann Bernoulli was one of the sponsors was sponsored by L'Hopital. So after discovering this, L'Hopital stuck his name on it, and it's forever been known now as L'Hopital's rule. So today's lesson, I'd like to do it in two parts. One, the concept, the idea, what's going on, what is it, how do we use it, why is it important, and then in the second part, we'll look at a bunch of examples. All right, so here we go. First, what exactly is L'Hopital's rule? Well, suppose we want to deal with a function, a particularly difficult function. Suppose I have f of x equals the natural log of x over x minus 1. And I want to know, what does this function act like? What is it? How does this function behave? The end behavior, x-intercepts, y-intercepts. Specifically, how does it behave around x equals 1? What is happening what's going on around x equals 1? Well, pretty quickly I can see that if I try substituting in 1, the natural log of 1 is 0. 1 minus 1 is 0. I get 0 over 0, which is undefined. It's one of those bad undefines. Now remember, when we did limits, we talked about this. And if it was an indeterminate form, if it ended up being 0 over 0, we knew that there was always some sort of trick that we could do to find out what the limit really was. So now we've done derivatives, we're going to go back and explore this same concept, but use the derivatives to answer all of our questions. So L'Hopital's rule deals in general with functions that are in the form some sort of, or if I want to look at the limit as x approaches sum a of f of x over g of x, some sort of rational function where the limit here is approaching 0 and the limit here is approaching 0 at a, so I get 0 over 0, or equally as bad could be something like infinity over infinity. There's a whole bunch of different bad versions of this. But the bad versions are actually good bad versions. There's certain ones that are called the indeterminate forms. So let's take a look at what L'Hopital's rule said, what Bernoulli said, and then we'll kind of rip it apart and talk about it, and then in the second part we'll apply it and see how it works. So here comes L'Hopital's rule. So L'Hopital's rule. Hospital. And L'Hopital's rule says that suppose F and G, suppose F and G are two different functions and they are differentiable. G is going to end up being my denominator here. So the derivative of g of x does not equal 0 near some point A, but it might at A. So the derivative doesn't equal 0 at some point A, except possibly at A. So except possibly at point A. And let's say that I know that the limit as x approaches A of f of x is 0, and the limit as x approaches A of g of x is also 0. Then you can see in this case I'm going to have 0 over 0. But L'Hopital says I could have other possibilities, or maybe the limit as x approaches A of f of x could be plus or minus infinity, and at the same time the limit as x approaches A of g of x could be plus or minus infinity. In that case, I'm either going to have 0 over 0 or infinity over infinity or something like that. Something very bad's going on. So those are my indeterminate forms. So what I'm going to end up with here is an indeterminate form. And right now the indeterminate forms I want to talk about are something like 0 over 0 or infinity over infinity, or that shouldn't be an equal sign, negative infinity over negative infinity. So something like this. These are my indeterminate forms. These are bad. We can't tell what these are. 0 over 0, infinity over infinity, negative infinity over negative infinity, or anything like that. These are all very bad. These are indeterminate forms. But they're good types of bad. If it's one of these indeterminate forms, then L'Hopital says we can find the limit. And here's what L'Hopital says. The limit, let me use a different color here. Let's see, what have I not used? I guess I'm going to use blue again here. So the limit as x approaches A of f of x over g of x, and notice I would have either 0 over 0 or infinity over infinity. I'd have one of these, is the same thing as the limit as x approaches A of the derivative of x over the derivative of g. And this is L'Hopital's rule. I can take the derivative of the top and the derivative of the bottom, and it would be the same thing. I would get the same, the limit there. And by taking the derivative, hopefully I'm going to get away from one of these different types of forms, one of these different bad types of forms. All right, so let's take a look at that first example that I put up on the board, and let's do this one, and then I'll break the lesson, and then we'll just do a whole bunch more examples. So in the first one, I said, well, what if I had the limit as x approaches 1 of the natural log of x over x minus 1. Now, the first thing, before I can use L'Hopital, I have to show that it's one of my indeterminate forms. L'Hopital only works if it's either 0 over 0 or infinity over infinity, or, as we'll see in the next part of the lesson, there are some other indeterminate forms where L'Hopital will work. But right now, those are the ones that I want to focus on. Those are the ones that we saw back in Chapter 2 when we did our limits. And clearly, if I do direct substitution here, I'm going to get 0 over 0. So this works. So L'Hopital says, well, I can do the derivative. This is going to be the same thing as the limit as x approaches 1 of the derivative of the natural log of x over the derivative of x minus 1. In other words, the limit as x approaches 1 of, what's the derivative of the natural log of x? The derivative of the natural log of x is 1, what is that going to be? 1 over x. And the derivative there is 1. So now I've got the limit as x approaches 1 of 1 over x. I can do direct substitution here. This is just going to be 1 over 1, which is 1. So the derivative of the, or the limit, I should say, of the natural log of x over x minus 1 as x approaches 1 is 1. All right, so when we come back, we're going to look at a whole bunch more examples, and we'll see that there are some other types of indeterminate forms.